Swayam Prabha. Digital India. Educated India.
Okay, let me continue on compressibility of soil under soil mechanics and geotechnical engineering. And this compressibility of soil, I have just taken one problem, and I have tried to show how to calculate void ratio corresponding to a particular pressure increase or at a particular pressure, and we have shown from the back calculation from the back. And after getting the void ratio and pressure, how to calculate coefficient of volume compressibility MV, I will continue and then I will show one or two methods again. So, let me this is the one we have tabulated previous lecture, that pressure versus this is actually your pressure, and this side is your void ratio. And this void ratio versus pressure, and perhaps it is asked to find out the coefficient of volume compressibility at the pressure range of 250 to 350. So, that means I have to find out first void ratio corresponding to pressure 250 somewhere here, and I may get some value somewhere here, and similarly 350 which is somewhere here, I will get the corresponding value from here. So, I will get V E 1 here, another E from here, another E from here. So, these two values of E we calculate estimate or read from this graph, and then I will go back to the equation for volume compressibility, and using that I can find out the coefficient of volume compressibility. So, let me see that. So, you can see that we have got from the EP curve corresponding to pressure equal to 250 kilonewton meter square, kilonewton per meter square pressure, we have got E equal to 0.666, and similarly at 350 kilonewton per meter square pressure, we have got E value equal to 0.658. So, it is decrease, because with the increase of void ratio with the increase of pressure, the actually soil will be compressing, and soil compressing means what it will happen, there will be reduction in void ratio. So, void ratio will be reduced. So, once you get these two void ratio, A is actually, if when you get a EP curve, E versus P curve, then you are getting A, that is slope of EP curve is A. So, that means you have got 2 points you have selected on the curve, 2 points you have selected on the curve. So, we have A equal to d by dp. So, d is a change of void ratio from this to this. So, 0.666 minus 0.658, and the change of pressure, that is from here to here, it was 250, it was 350. So, 350 minus 250, it is 100. So, that means d by dp is this one, and dE by dP. So, it will not be kilonewton per meter square, this will be by kilonewton per meter square actually. So, mv equal to A by 1 plus E 1, that is the formula we have expression we have derived the last class, A by 1 plus E 1. So, A value is this, and 1 plus E 1. So, this is 1.666. So, it is nothing but 1 plus E 1, E 1 is 0.666. So, then we are getting this one, and this unit of MV will be same as A. So, it will be meter square per. So, here actually wrongly written, it will be meter square per kilonewton, this is also meter square per kilonewton. So, or it is 1 by kilonewton per meter square. So, this is the value we are getting by one method. There are several other ways it can be calculated. So, this is the first one. So, that means you pressure versus thickness if you get, then from there pressure versus thickness means what? We are, as we have mentioned that if I apply the pressure on the soil, some certain amount of soil, under this pressure soil will undergo consolidation, and this consolidation means what? Under this pressure, when the compression will continue, when you will see there is no change of thickness, that means compression is complete under this loading, that is then under that loading compression is or consolidation is completed. So, like that second level of loading, third level of each level of loading you have to see till there is no change of thickness. So, from there actually at the end point every time corresponding to each pressure we are getting at the end what is the thickness. So, that thickness versus pressure if you know, then from there we can find out void ratios, and there is a method we have mentioned already, and in the previous lecture I have prepared the table, and then from the tabulated data pressure versus E we have plotted the E versus P curve in the previous slide, and then from there previous E versus P curve we read at a particular pressure what is the E and two pressure. So, two E values will be there, and expression of d by d A is d by dP, and so this change of void ratio by change of pressure, and then you get this one, and mb is A by 1 plus E 1. From there we are getting a your coefficient of volume compressibility. Now, I will try to show another method, in fact two methods, same problem, since this problem is there in the previous lecture. So, you may forget. So, because of that I have brought once again, this is pressure 0, thickness this, 50 is thickness, the 100, 200, 400, 800 and 0, up to 800 pressure is increased, and we have allowed to compress over the sufficiently long time, and we have observed the final thickness. So, that means 800 pressure corresponding thickness is this, 400 pressure this is the corresponding thickness, 200 pressure this is the corresponding thickness, 100 pressure this is the corresponding, like that we have got. So, we have expression d by dP, two different ways can be done. So, that actually I will show in the next slide. You can see that mv expression can be written in this form. Actually, mv equal to volumetric change divided by pressure unit pressure change. So, you can see volumetric change is this expression also we have shown, this is also volumetric change. If I see compression is only vertical direction, so A constant, so throughout, then dH by H1 is a volumetric change, that means change dH over original thickness H and divided by dP. So, this one if little simplify, then 1 by H1 into dH by dP. So, dH by dP means what? Actually we in the previous method what we have tried, we have tried to calculate for a particular pressure what was the thickness, and based on that thickness what was the corresponding void ratio, each stage what is the void ratio we have calculated. But here we can see that there is a way out without calculating void ratio, directly based on thickness also we can do the mv calculation. So, you can see ultimately mv equal to 1 by dH by dP. So, dH by dP is the slope of the sample thickness versus pressure. See, dH by dP means sample thickness versus pressure. So, we are changing the pressure, and because of the change of pressure thickness is changing. So, that if you plot, and slope of that will be nothing but dH by dP. Hence, mv can be obtained by finding the slope of the curve at the required pressure and dividing by the original thickness. The thickness versus pressure curve is shown, I will show in the next slide, and H at, that means thickness H at 250 kilonewton square is this much, and thickness at 350 kilonewton square this much. So, del H, actually 19.28 minus 19.18 and 19.19, and your del P is del H by dP, this is del H 19.28 by 19 del H, and this is dP divided by original thickness. So, H 1. So, 19.28. So, this is the one. If you do, then you can see we are getting this. So, before doing that, I will show I will show the curve for thickness versus pressure. It is almost similar to that void ratio versus pressure. So, I will go back to that. Before that, I will just from the curve, rather from the plot, corresponding to pressure 350, thickness is this, corresponding to pressure 250, thickness is this. So, if this is the thing, we have to find out MV in the pressure range of 250 and 350. So, 250 and 350, what is the change of pressure? It is 100. So, del P is 100, and what is the, because of this change of pressure, what is the change of thickness? Whatever was originally 19.28 and now become 19.19. So, difference of that will be del E and sorry del H, and del H by original thickness. 19.28 was the original. So, this is the calculation 4.7 into 10 to the minus 5 meters per meganewton. Now, if you know the MV and calculation of settlement, already I have mentioned that delta will be equal to MV into del P into H. So, what are those? What is the pressure increase? What is the thickness and MV? So, all three if you multiply, then you will get the consolidation. If the 20 meter thick layer subjected to this pressure increase, that means 100 pressure is increased, the consolidation settlement would have been, you can see this is the MV and this is the thickness and this is actually your pressure increase. So, this is del P, this is H and this is MV. So, that all together and that will come in meter. So, to convert it to millimeter, I have multiplied by 1000. So, it is becoming 96 millimeter. So, that means 20 meter thick layer with this MV value, if you apply the load in such a way that in the middle of the clay layer the pressure increase is 100 kPa, then expected consolidation settlement is 96 millimeter. So, this is the simple expression. When the MV is there, using MV, calculation of settlement is very simple. MV multiplied by pressure increase multiplied by total thickness. Okay. So, let us go to next slide. Next slide is as I have told you that I will show you the void. This is actually thickness and this is actually pressure. So, pressure versus thickness plot, and whatever I have done, 250, this is the 250. So, corresponding thickness we have got, and this is about 350, corresponding thickness I have got. So, 19.19 here and 19.28 here, something we have got. So, these two pressure, that means we are getting the expression 19.28 minus 19.19 divided by 19.28 to 100. This will be in meter and multiplied by 1000, that will give you millimeter. So, 96 millimeter. So, this calculation is shown in the previous slide, but how to do it? Directly consolidation test, we are getting at the end of each pressure increment, what is the thickness we know. So, that thickness, so at the end of suppose 200 pressure, what was the thickness I have plotted. At the end of pressure application, at the after application of the 400 pressure, at the end what is the final value, this is the value. So, like that if you plot and finally join them, that is giving you thickness versus pressure curve. So, this is again whether you do from void ratio or from this, they are both actually similar almost. So, dH by dP or dE by dP we are using. So, once actually we are using directly thickness, once actually because of this change in thickness, what is the void ratio change, that is the thing we have done. Now, we have one more method, equivalent solid height you may calculate, and based on that we can do some calculation, that is something like this. So, before going to this, there is some remark. The practice of working back from the end of consolidation test, that is well accepted, because when you put a prepare a sample and put in the consolidating meter, it is not guaranteed that it will be saturated, but if I complete the test and at the end of the test, this is only submerged condition, if you allow to expand actually with 0 loading, then that time it is expected that soil will be saturated. So, that is the one we utilize, that at the end it was saturated, and what is the final thing, from there I get void ratio, and then we are going back to the original. So, that is the one calculation we have done, though it is obviously because of this advantage, people are it is well accepted method. But obtain a EP curve by working from the original thickness, that means we have got from back to front. Now, we suppose some may prefer from directly from this to this, because it was the first void ratio and this was the last void ratio. I will first find out the first one and last one will be that last. So, that way also it can be calculated. So, to do that we have to do some calculation, and you can see this is the calculation E. Actually, from the definition, E is the VB by Vs, and VB is actually nothing but total void minus total volume minus Vs, and if I keep constant cross sectional area, then you can see, suppose the sample is soil is something like this, and under pressure it is compressed, suppose like this. So, this much compression took place, thickness changes, but this cross sectional area suppose kept constant. In that case, V minus Vs by Vs, that I can write A times H is the total volume, A times H is the total solid volume, and A into H is again total volume already. So, I can imagine this soil. Initially, this is Vs and this is void. So, this Vs will have a height, suppose Hs. So, A times Hs, and this will be this, then if you simplify, it become H minus Hs by Hs, the void ratio. So, where A is the cross sectional area, H is the thickness of the sample, and H is the equivalent thickness of the solid. Now, again Hs equal to actually rho W Gs, A into Hs is the volume multiplied by unit weight will give you the weight, or volume multiplied by mass will give you the mass. So, that is what actually Hs equal to total mass divided by rho Gs by A, rho Gs into A. So, that way Hs can be calculated by this, if you know the mass, rho Gs into A, or we can say the volume A into Hs will be m by rho W Gs, and so Hs if I take, then Ms rho W Gs into A. So, this way actually if I know the weight of the mass, if you know the mass and if you know the weight density of water you know, and Gs of soil, most soil is known, or if it is not known, we can assume 2.65 to 2.7 that cross sectional area. So, this is the way one can calculate the Hs. So, this actually to be used in the calculation of void ratio in other methods. You can see now, if I want to do this problem by alternative method, we obviously require some additional information, and this additional information is really not additional information. During the test we have those information. So, initial problem, those information not given, because that are not essential. If I want to do based on void ratio or thickness E versus P curve if you use, or your thickness versus pressure curve if I use, then your this calculation that means this information was not needed. Now, if I want to this method, we require this information. Suppose this information available, suppose it is like this. The sample diameter was 3 inches or 75 millimeter, thickness was 20 millimeter, and your mass of the sample after drying, actually it was 135 gm, 35.6 gm gram. That means, after completion of the test, we have kept it in the oven and then dried, and dry volume was 135.6. So, MS become 135.6 and A become, the since area is given pi by 4 into 75 square. So, this millimeter square. So, HS become 1 is the rho W, 2.65 suppose this, and this is area, 135.6 by this become HS, and if you want to convert into millimeter, then you are getting multiplied by 1000. So, 11.58 is the thickness of the equivalent soil mass thickness. So, if there is a total soil, whatever may be the thickness, out of that, out of 135 gram soil, and if that is the diagram. So, diameter is mentioned and the thickness also mentioned, total thickness, and out of that, if it is dry weight is this. So, what is the equivalent HS? That means, HS, when you are considering HS, that means you are considering this as a solid, there is no void in it. Whatever solid is there, I am actually theoretically I am putting together. Then if it is a total solid mass, what is the equivalent height? That is the thing, based on that calculation it came 11.58. Then E will be from the derivation in the previous slide, we have shown H minus HS by HS. So, this one actually can be used to calculate void ratio at any pressure range starting from beginning. So, that is the thing done in the next slide. You can see here 0, pressure is 0 and pressure is 0, the thickness is this. So, what is the void ratio? This void ratio H minus HS. So, H minus HS, H was actual H was 20 minus HS 11.58 divided by HS 11.58. If you do this calculation, then you will get the void ratio equal to this. Similarly, it is 19.65 minus 11.58 is constant everywhere divided by 11.58. This is the one you get. If you calculate, then you will get 0.697. Similarly, here 19.52 minus 11.58 divided by 11.58, there also you will get this value. Similarly, here 19.35 minus 11.58 divided by 11.58, we will get this value. Similarly, for this 19.15 divided minus 11.58 divided by 11.58, we will get this value, and here you will get 18.95 minus 11.58 divided by 11.58. So, if you do this, then you will get this void ratio. So, now we have got again void ratio, and using this void ratio and this pressure, you can draw EP curve, and from there you can get the volume compressibility, and you are getting you can see this is a practice problem, and the problem whether it is if you take a true experimental data, then your value may not be so close, but here actually to explain this is all you can say just data taken, and it may not be the experimental data, and so here actually you get that theoretically all are giving same results, by and large same results. But if you do experimental use experimental results, you may get some variation. In that case, you have to take the judgment and put the appropriate value based on your own judgment. Now, here actually the you have to find out final compression some other way also. that MV method we have discussed now. Now we will be measuring compression method, compression index method, and for that you have to observe the clay behavior under loading, behavior of the clay under loading, or consolidation behavior of the clay under loading, and for that you can see that the clay is generally formed by the process of sedimentation from a liquid in which the soil particles were gradually deposited and compressed as more material was placed above it. Suppose there is a flowing fluid and soil is deposited here. Today the thickness was this, tomorrow is like that. So, it will be accumulated, height will be increased. So, if I do, then under this loading this soil below will be consolidated. So, like that, this is the process, and the EP curve corresponding to this natural process of consolidation known as virgin core. So, this is the natural way consolidation. So, if you do E versus pressure corresponding to that, then whatever you get, that is called virgin compression curve, and this curve is approximately logarithmic actually this curve is approximately logarithmic, that if the values are plotted to a semi-log scale, that means E versus P you are getting this, but if I put E versus log P, then we get a straight line like this, and this is actually P1 P2 means it is log P1 log P2, okay, and here actually if I put it in the log scale directly I will put the values, or if it is a linear scale and then you have to calculate log P1 log P2, then you have to put it. Generally we use semi-log graph, and then if you use semi-log graph, then you will see that P1 P2 directly read from there, and then E1 E2 you read directly from here. So, E will be equal to E naught, here actually E1 E2 in terms of E1 E2. So, E1 will be E2 will be equal to E1 minus Cc into log 10 base P1 plus del P by P1. So, this is the way one can write the equation, since this is written in general form P naught, that means that the originally when that is P naught and then del P, but here in this plot we have shown in terms of E1 and E2, then if you put in this way, then E2 equal to E1 minus Cc into this form you can write. And you can see the compressibility, this E versus P curve generally will have some point here and there, this is continuous, but if you extend this curve it will meet somewhere else. So, there is a mechanism, and if I put corresponding curve in the log scale up to this is a straight line compression line, this there is a small curve. Why it happens actually? This is actually when this is suppose originally consolidated reached up to this, and while sampling, because of the decrease in pressure or pressure release, it may volume expand may be there. So, if it may reach there. So, when I will load again, it will compress in the different way instead of this way, it will different way, and when reach A, and then if you load further, then it will be smooth line which actually like normal consolidation. So, beyond that actually it was a recompression, and because of that if we put this data, so this data B, A and C, this data you put in a log scale, then up to A you will get a small curve, and then A to C you will get a straight line, because we know that the behavior is actually logarithmic. So, this one once again explained here a normally. So, compression curve for a normally consolidated clay, you can see here I have already defined perhaps during shear strength chapter what is normally, what is consolidated, over consolidated, because I have mentioned that time that the behavior will change because of this. When if it is a normally consolidated soil, the behavior is something, and over consolidated soil behavior is different from that. So, now once again I am repeating, and I have also mentioned that appropriate place I will repeat it and I will explain why it is different. And you can see a normally consolidated clay is one that has never experienced a compression or consolidation pressure greater than that corresponding to its present overburden pressure. Suppose at a particular site I can calculate present overburden pressure, but if the history of the soil layer never been subjected to higher pressure than this, that means this is normally consolidated, that means this is consolidating uniformly, it is never consolidated by a higher pressure. And the compression curve of such soil is shown, the figure I have shown there, and the clay was originally compressed, the figure whatever we have shown, the clay was originally compressed by the weight of the semi material above along the virgin consolidation curve to some point A. So, that the point I have shown from the vertical axis to up to A, that is actually the point. Owing to the removal of the pressure during sampling, the soil has expanded to a point B, that I have shown. I will show once again. Hence, from B to A the soil is being recompressed, that is recompression, whereas from A to C is a virgin consolidation curve. So, semi log plot corresponding to this shown is the figure. So, that means I will show you the once again that one. So, you can see here, as I have mentioned here, this is the path reached up to this, and suppose at this point the existing overburden pressure there, and but suppose it is a 10 meter depth, and from 10 meter depth I have taken the sample. When you have removed the sample, then there is a pressure release. Because of that, suppose the volume, the sample is increased to a volume, suppose reached here. Now, if I start pressurizing from here, so up to this, it is a recompression, and from when pressure increase beyond this, then normal consolidation, that is actually your virgin consolidation. So, this curve if you plot when in the log scale, you will get up to A the little curve and then straight line. So, this is about the behavior of consolidation, normally consolidated soil, and that is all. I will take now over consolidated soil and their behavior and how to use the consolidation settlement using that in the next slide, next lecture. Thank you.